Hello, good evening everyone. Welcome to this amazing session of Power Hour. We have been already uploading so many live classes and I hope you all are enjoying that. So today I am here to have a session on the concepts and problems on simple harmonic motion oscillations, right? And we'll be doing some part of wave also. So I'll be taking a few important concepts and questions of the topic oscillations and wave. And I hope you people are going to enjoy that. So tell me fast, comment box, write a message in the comment box. Am I audible clearly? Am I visible clearly? So shall we proceed now? So I'm waiting for your response. Do it fast. Shall we start now? Am I audible? Yes, come on, join fast. And today we are having a very auspicious occasion of Eid, so I wish you all a very happy Eid. Eid Mubarak to you all, and hope this Eid you all are enjoying with your family members and with your loved ones. So keep enjoying with your family members. Spread all the positivity, love and happiness in your surrounding. So Eid Mubarak to you all people. So just we are going to start. Let me check with my network. Yeah, good to go. Good to go. Yes, I can see. We are going good. So fine. I will be starting now the topic on simple harmonic motion and oscillation. So it's a very easy topic and I'll be writing all the names. As you can see in the topic, the name is written oscillation, so I'll be doing oscillations today. So what are the subtopics that we have to understand here? So I'll be taking my favorite pen with yellow color. So we have to understand oscillations, right? Then writing amplitude, displacement, velocity, acceleration for a particle performing SHM. So whenever we are dealing with the topics like topics with oscillations, we must be able to write down the displacement, velocity, acceleration of the particle performing SHM. We should be able to see its amplitude, time period and all. So we generally been asked to find out the time period of oscillation. And this concept will be utilized in all different topics also. Like sometimes if you'll see in electrostatics, you are supposed to find out the oscillation of the time period if the charged particle displays perpendicular to its plane. And in gravitation also, you can see some of the questions where you are asked to find out the time period of oscillation. So we'll understand basically what are the concepts where we have to find out the time period and all. Then we have to write down the energy of the particle performing oscillation, like potential energy as well as kinetic energy. You have to find out potential energy. You have to find out the kinetic energy. So I'll explain you how to write down all these topics. So I'll be mentioning these topics now. So just see here. In oscillation, what is important is the particle is going to perform to and fro motion about a fixed position, okay? The particle is going to perform to and fro motion about a fixed position, okay? About a fixed position. And you know that this fixed position is known as mean position of SHM. This is known as mean position of SHM. So the point about which the particle performs to and fro motion is what we call as fixed position, or we call the mean position of SHM. And what is that? How do we identify this mean position? At this point, F net on the particle should be 0. This is important. At mean position, the net force acting on the particle should be 0. It should not be experiencing any force. So basically at this point, the particle is in equilibrium, okay? The particle is in equilibrium. And in work energy power chapter, we have understood that we can have 3 types of equilibrium: stable equilibrium, unstable equilibrium, and neutral equilibrium. So any one of you can tell me what type of equilibrium it is. Here at mean position, the particle is in equilibrium, so definitely the net force acting on the particle is 0. But what type of equilibrium point it is? Is it a point of stable equilibrium, or it is a point of unstable equilibrium, or it is a point of neutral equilibrium? If someone is watching online, they can write down the answer in the comment box. I will give you a chocolate for that. Yeah. So the correct answer is stable equilibrium. So the particle is in equilibrium, and this is a point of stable equilibrium. Stable equilibrium. And what is important about stable equilibrium? That whenever we disturb a particle from the position of stable equilibrium, then it will come back to the same point again. So if we have, let's say, this point as the point of stable equilibrium, and I'm having a particle here. So if I displace a particle toward the left side and I release it, it will again come back to this point. If I'll displace the particle toward the right side like this, the particle is displaced toward the right side, and when I'll be releasing it, again it will come back to its initial position. So from the point of stable equilibrium, if we'll displace a particle slightly, then it will again eventually it will come back to its original initial position. So this is the property of stable equilibrium. So if you disturb a point from stable equilibrium, then it is going to come back eventually to the initial position, okay? So if the particle is coming back to its original position, it means what? It means that there must be some force acting on this particle which is bringing back the particle to the initial position. And what do we call it? We call it as a restoring force. So it becomes a very, very important part, that whenever we are dealing with the oscillations, or whenever we are dealing with the simple harmonic motion of a particle, then there should be a mean position defined, and when the particle is displaced from the mean position, then eventually it will come back to its original position, and the force which is responsible for bringing back the particle to its mean position is known as restoring force. So which force is responsible for bringing the particle back to the mean position is restoring force. So any force can act like a restoring force in different circumstances. So restoring force is not a new force. Any force in that situation can, in different situation, you will find that different forces are behaving like a restoring force, okay? Sometimes the gravitational force can act like a restoring force. Sometimes electric force can act like a restoring force. Sometimes the spring force will also behave like a restoring force. So in different circumstances, different experimental setups, different forces can act like a restoring force. So till now we have discussed that when we talk about SHM, we encounter a fixed position, mean position. F net should be equals to 0, particle should be in equilibrium, it should be a point of stable equilibrium. And since it is a point of stable equilibrium, there must be a restoring force acting on it. And this is the force which brings back the particle to its mean position when it is slightly displaced from its position. So now you can understand that if we have this straight line, the particle is over here. So this is my particle, okay? So when I'll displace this particle left and right, eventually it will start moving like this to and fro about this mean position, and eventually it will come back to its original position. So there are few assumptions that we are going to discuss. That initially I am considering that there is no loss of energy. There is no loss of energy. And when there is no loss of energy, such oscillations are known as undamped oscillations, okay? This type of oscillations are known as undamped oscillations. So in NEET we have to study only about the undamped oscillations. Damping is not into the syllabus of NEET. So those students who are preparing, they can make a point of this, that in NEET exam there is no question asked from damping oscillations, okay? So you may ignore that topic. You can study that topic out of your interest, but you can do it later on. So till NEET exam, you should focus more on undamped oscillation. So there in undamped oscillation, there is no loss of energy, and we are talking about undamped oscillation. So when there is no loss of energy, I can understand that we have a very important concept that we can use. That is, we can use the concept of energy conservations. So if there is no loss of energy, we are talking about undamped oscillation. I'll be using the concept of energy conservation. I'll be using mechanical energy conservation, okay? Summation of kinetic energy and potential energy should be constant throughout. So these are the important things that I'm telling you. So we will be using energy conservation. And one equation will be using for F net equals to 0. Net force acting on the particle is 0. Energy conservation is applicable in such situations. Now coming to the next slide. That now when this particle is there, and when it is displaced toward the right side by a small displacement x, and I'm considering this direction to be positive and I'm considering this direction to be negative. So when this particle is displaced toward the right side from its mean position, okay, from its mean position, then what will happen? Immediately a restoring force will start acting on this particle, and let's say that restoring force I am representing, when the particle is located here, the force will be acting on this particle toward the left hand side or toward the mean position, and we'll be calling this as restoring force. And now if it is performing oscillation and if it is performing simple harmonic motion, so it is a specific condition for simple harmonic motion that if a particle performs SHM, simple harmonic motion, then it should follow this condition that restoring force should be proportional to what? It should be proportional to minus x, or you can call it the displacement restoring force should be equals to what? Minus k into x. Restoring force acting on the particle should be equals to minus k into x. What is k here? What is k here? This is what? SHM constant. This is what? SHM constant. And x here represent the displacement from the mean position. It represents the displacement from the mean position, okay? It is representing the displacement from the mean position. Now we'll quickly understand that oscillations and SHM, are they same thing or they have any difference? Okay, so you should understand that all oscillations are not SHM. All oscillations are not SHM. In all oscillations, the particle will be performing to and fro motion. So whenever particle starts performing to and fro motion about the mean position, we will say that the particle is performing oscillations. The particle is performing oscillations. So when the particle is performing oscillations, so the restoring force acting on the particle will be such that it can be written as restoring force equals to what? Minus k into x raised to the power of n. X raised to the power of n. Now when I'll be putting x equals to n equals to the value of n to be 1 or the value of n to be 3, or I'll be putting the value of n to be 5, say let's say odd numbers. If I'm putting it to be odd numbers, right? So then what will happen? We'll see that we'll find out different equations of restoring force. But out of all these conditions, when the restoring force is linearly proportional, when it is linearly proportional to the x power 1, so this is the specific condition for SHM. So if we have the higher values of n, in those conditions it can be oscillation, but we will not call it as SHM. So as the name suggests, simple harmonic motion. So simple means what? The restoring force is linearly proportional to the displacement of the particle. So this is very, very important, that all the oscillations cannot be known as SHM. But out of all the oscillations, only one particular conditions will be calling as SHM, when the restoring force is linearly proportional to the displacement of the particle, okay? So in SHM what will happen? Restoring force is linearly proportional to the displacement of the particle from mean position. So let's say कि sometimes we are having that restoring force is proportional to the third power of displacement or the fifth power of displacement. In all such situations, the motion of the particle can be known as oscillations, but it will not be considered as SHM. So in our syllabus, we have to study only about SHM. Okay, for higher powers of n, for higher values of n, we don't have to study. So our syllabus is limited only to SHM. So you should keep that in mind. Okay. So now we have got, whenever a particle is performing SHM, then restoring force should be linearly proportional to the displacement of the particle from the mean position. So from this equation you can see that when the particle is displaced toward the right hand side, the value of x will be positive, and then negative is already here. So the direction of force will be toward the negative side. So when the particle is displaced toward the right side, the restoring force acting on it should be toward the left hand side. When the particle is displaced toward the left hand side, so the value of x is already negative, and outside there is all one negative there. So negative and negative will become positive, so the direction of force is positive. So when you displace the particle toward the left hand side, the force should be acting toward the right hand side. So we are getting the correct answers from this equation. So this is our important equation for SHM. So this becomes our important equation of SHM. We'll be using it further. Now just see here. So when we have this force equals to minus k into x, this F is equals to what? Minus k into x. So you know that the net force acting on the particle having constant mass, that can be written as mass into acceleration, and that is equals to minus k into x. And from here we can say that A equals to minus k by m into x. This is acceleration of the particle is also proportional to, directly linearly proportional to the displacement of the particle from the mean position. So if we have this as the acceleration of the particle, and we know that acceleration of the particle can be written as second derivative of the displacement, and that is d2x upon dt square plus k by m into x equals to 0. So this is known as differential equation of SHM. Okay, this is known as differential equation of SHM. This is known as differential equation of, this is the differential equation of SHM. Now comparing this equation with the general equation of SHM, I can say that this should be d2x upon dt square plus omega square x should be equals to 0. So comparing, then we are getting omega equals to what? Under root of k by m. So from here we get a very important formula, that if a particle is performing SHM, then its angular frequency omega should be written as under root of k by m, where k is the SHM constant and m is the mass of the particle. Yeah. Now just look at here. We know that omega can be written as 2 pi by t, where t is the time period and this is k by m. From here we can say the time period equals to what? 2 pi under root of m by k. So this is how we can find out the time period of SHM, time period of the particle performing SHM. T equals to 2 pi under root of m by k, where k is the SHM constant. So in all situations where we are required to find out the time period of oscillation, we will be finding the SHM constant in that situation, and we'll put the value of SHM constant here, and directly we can get the time period of oscillation. I'll pick up some examples, I'll pick up some questions where I can show you that how we are going to find out the time period of oscillation. So simply in that particular situation you have to write down the force equations, you have to find out the value of SHM constant, then put it here, and directly we'll get the answer for this one. And since we know the time period, we can also calculate the frequency. Frequency is what? This is 1 upon time period. Okay, so I can say this is 1 by 2 pi under root of k by m. So likewise this we can find out the frequency of we can find out the frequency of oscillation. Okay. Yeah. So I hope this is clear. To find out the acceleration, to write down the force, to find out the time period, and to find out the frequency of oscillation. So once we are done with this, I'll tell you one more thing. So when we have this differential equation d2x upon dt square plus omega square x equals to 0, this is the differential equation of HHM, and solving here for x, I'm getting general solution is x equals to a sine omega t plus phi. By solving this equation, we get the value of x to be a sine omega t plus phi. So this equation represents the displacement of the particle performing SHM. So I can call it as the general equation of displacement for the particle performing SHM. X equals to a sine omega t plus phi. You already know that a is the amplitude of the oscillation. This is amplitude of the oscillation. And since we are talking about the undamped oscillation, this amplitude have to be constant. Okay, this will remain constant throughout the oscillation of the particle. It will not change. Omega is what? Omega is angular frequency. Angular frequency, and this represents the time. So this x represents the instantaneous position of the particle at any given time t. So if you will put t equals to 0 here, if you are going to put t equals to 0 here, this term will become 0, and this will be a sine phi. So the particle is located at a position of a sine phi when the time is 0. Okay. So when you will put t, some value for t here, is at that instant the disposition of the particle will be given as a sine omega t plus phi. So this represents your SHM equation. So phi is what? Phi is your initial phase. Okay. Phi is your initial phase. This quantity omega t plus phi, this entire term omega t plus phi is known as total phase of the particle. Total phase of the particle. Okay. This is phase. So putting t equals to 0, I will be getting the initial phase. So you can see here that when I am putting t equals to 0 here, this term will reduce to only phi. Okay. So phi is your initial phase. So at time t equals to t1, the phase will be omega t1 plus phi. At time t equals to t2, the phase will be omega t2 plus phi. Or at time t equals to t3, the phase will be omega t3 plus phi. So by changing the value of t, I can get the different values of the phase of the particle. Okay. So this entire quantity is known as the total phase. Putting t equals to 0, I will be getting the initial phase. Okay. So this is how we can represent this thing. So x equals to a sine omega t plus phi is the general equation of the displacement of the particle performing SHM. Once we know the displacement of the particle is, a sine omega t, and I have assumed that phi equals to 0, means initial phi is 0. Okay, I have assumed that. This is my assumption. Okay, that the initial phase phi equals to 0. So the equation of the displacement of the particle can be written as x equals to a sine omega t. This can be written as x equals to a sine omega t. Okay. Now, if we know the equation of the displacement of the particle, very easily we can find out the velocity of the particle and the acceleration of the particle. So let's do that. Differentiating this equation with respect to time, I am getting dx by dt, and here a is constant, it will remain outside, and the differentiation of sin theta is cos theta, so it is cos omega t, and then coefficient of omega is there, so you have to multiply here. So dx by dt equals to what? A omega cos omega t. So dx by dt represent the velocity of the particle, and it is a omega cos omega t. This is the velocity of the particle which is performing SHM. Okay. So once we have written displacement, we have also written the velocity of the particle. Now you can see here that the displacement of the particle is a function of sine, and the velocity of the particle is a function of cos. So if you want, you can also convert this function in terms of sine. Then it will be easy for you to compare the phase of the two two quantities, displacement and velocity. Like if one quantity is sine, the other quantity is cos, then directly you cannot compare their phase. Okay, so when you are comparing the phase, try to make the function same. Okay, if one function is sine, so make the other function also as the function of sine. If one function is cos, you try making the other function also in terms of cos. So when both the functions, displacement, velocity, will be in terms of sine, or they will be in terms of cos, then it will be easy for you to write down the phase difference. Okay, otherwise you might ending up making a mistake. Okay, so try to avoid that. Whenever you have to compare the phase, try writing velocity, acceleration and displacement all in terms of same function, be it sine or be it cos, doesn't matter. So what I am going to do here is a omega cos theta can be written as sine omega t plus pi by 2. Okay, sine 90 plus theta is what? It's cos theta. So sine pi by 2 plus omega t is what? Cos omega t. So velocity can be written as a omega sine omega t plus pi by 2. So this is how we can write down it. So once we know the equation of displacement, we know the equation of velocity, I can also find a equation for acceleration. Differentiating this equation one more time, differentiating v with respect to t, I am getting what? Left hand side I will be writing dv by dt, and toward the right hand side I know this is a omega, so it is constant, and differentiation of cos theta is what? Minus sin theta. So it is minus sin omega t, and the coefficient of t is omega, so I am going to multiply here. So dv by dt is acceleration, and this is minus omega square a sin omega t. So I have also written the equation of acceleration of the particle. So this is the equation of displacement, I am writing this equation number 1. This equation of velocity, I am writing this equation number 2. And this is acceleration equation, so I am writing this equation number 3. So I have written the equation for displacement, velocity and acceleration for the particle performing SHM. Now if you will see closely, then you will find that this a sin omega t can be written as what? X. So you will find that acceleration is minus omega square x. This is also one way of writing this. So you can write acceleration as a function of time like this, or you can write down acceleration as a function of position, a equals to minus omega square x. So you can either write acceleration in terms of time, or you can write acceleration in terms of the position. Same here, you have written velocity as a function of time here. If required, you can also write down velocity as a function of position. How you are going to do that, I will show you. Okay, see this one. Velocity is written as a omega cos omega t can be written as 1 minus sin square omega t. Okay, cos, by using the identity, I know that sin square theta plus cos square theta equals to 1. So cos theta can be written as under root of 1 minus sin square theta, and we know that sin omega t equals to x by a. So it can be written as a omega under root of 1 minus x square by a square. So I can see here just a little bit of calculation. A omega under root of a square minus x square, and divided by a square, it will come out and a will get cancel. So I have got one more equation, that velocity equals to what? The velocity equals to omega under root of a square minus x square. So I have also written velocity as a function of position. So velocity is a function of time, velocity is a function of position, acceleration is a function of time, acceleration is a function of position, and displacement is a function of time. So these 4 plus 1, 5 equations are very important, and by using these 5 equations we can calculate so many things. Almost all the questions that we have been asked in exam, that can be solved by using these equations. Okay, yeah. So 1, 2, 3, Then this is equation number 4, and this is my equation number 5. Now just looking at this equation, I'll figure out some important and interesting facts. This is x equals to 0. This is my mean position. I'm considering x equals to 0 to be my mean position, okay? So let's say when the particle is going in this direction, the restoring force is acting in this direction. So basically this is trying to reduce the speed of the particle. This force is trying to reduce the speed of the particle. So there will be a point where its velocity is going to be 0, and at this point the velocity becomes 0, and that's the reason I'm calling it as an extreme position. Extreme position, okay? Same thing will happen when the particle is going in this direction. Acceleration will be acting in this direction, okay? So this force is also reducing the speed here, and gradually the speed of the particle will keep on decreasing until it becomes 0 at this point, and so I'll be calling this as extreme position. So you can see this is extreme position, this is also an extreme position, and this is your mean position. I'm calling mean position to be O, and I'm calling this extreme position to be A, and this extreme position to be B. So how the particle is moving? It is going from O to A, then it is going from A to O, it is coming back from A to O. So while the particle is coming from A to O, then what happens? When the particle is coming from A to O, this is the direction if the particle is moving, and this is the direction in which the force is acting. So you can see that velocity and acceleration both are in same direction. The particle is going to speed up. So while the particle is coming from A to O, its speed is increasing till the point O. Once the particle crosses the point O, its velocity is in this direction towards B, but the force is acting towards O. So again particle starts decreasing its speed, and finally it comes to rest at this point B, okay? So when the particle is coming from A to O, its speed is increasing up to this point O, and once it crosses the point O, its speed starts decreasing, okay? It starts deaccelerating, okay? It starts retarding. From O to B it starts retarding, and at B its velocity becomes 0. So from O to A, the motion is what? Retardation. The particle is slowing down. From A to O, it's speeding up, okay? It's speeding up. Then going from O to B, again it is retarding, okay, or slowing down. And while coming from B to O, you can see the directions. When the particle is moving from B to O, this is the direction in which the particle is traveling, and this is the direction in which the force is acting. Because I told you earlier that force is always acting toward the mean position. Do remember that, okay? Force always acts toward the mean position. So when the particle is coming here from B to O, in this direction particle is coming from B to O. So velocity direction is towards O. Acceleration is also acting towards O. So velocity, acceleration are having the same direction. The particle will speed up. And it will speed up till it reaches the point O. Once it crosses the point O, it starts retarding, okay? Because again, O to A, retardation will be there. So when particle has gone from O to A to O, O to B, and B to O, we'll call that one oscillation is completed, okay? One oscillation is completed. One oscillation is completed. Or we can call that one cycle is completed, okay? One cycle is completed. One oscillation is completed, or one cycle is completed. It's the same thing. It is the same thing. So whenever the particle is traveling toward the mean position, it is accelerating. Whenever the particle is going away from the mean position, it is retarding. So what is the point where you will get the maximum speed? It's a bit logical, you can think of it. I've already explained the entire situation. So now you can tell me what is the point where the particle will have the maximum speed. So When the particle is going away, its speed is decreasing. So definitely O is the point where the particle speed is maximum. So at point O, particle speed is maximum. Particle speed is maximum at this point. And here the particle speed is maximum, it means that the kinetic energy is also maximum at this point. So kinetic energy is also maximum. Kinetic energy is, and at the extreme position, kinetic energy equals to 0 and potential energy will be maximum. Again at this point, this extreme position, kinetic energy equals to 0 and the potential energy will be potential energy maximum. Okay, I hope you are getting this point. So I have explained you the entire situation, that what is that point where the velocity will be maximum, what is the point where the kinetic energy is maximum, what is the point where the potential energy is maximum, what is the point where the potential is minimum. Everything is explained. Initially I told you that this is the point which is the mean position, okay, and if it is mean position, this have to be the point of stable equilibrium, and since it is the point of stable equilibrium, and we know that at stable equilibrium potential energy is equals to potential energy minimum. So at mean position you will find the minimum potential energy and maximum kinetic energy. At the extreme position you will find the kinetic energy to be 0 and you will find out the potential energy to be maximum. So while the particle goes from mean position towards extreme position, its potential energy is going to increase. Here also the potential energy is increasing and the kinetic energy is 0. And since there is no damping, the total energy have to be conserved. So if you will find out the total of both the energies, kinetic energy and potential energy at any point during its SHM cycle, you will find that to be a constant. So if you have any doubt till here, you can write down in the comment box. I'm waiting for your responses. Okay, moving ahead. So if we have written this much of things, so I'll write kinetic energy of the particle. So kinetic energy is half m v square, okay, half m. What is v? V is what? A omega cos omega t. Do you remember that? V is what? A omega cos omega t. A omega cos omega t. A omega cos omega t and square, okay. So this is half m a square omega square cos square omega t, okay. So this is kinetic energy of the particle performing SHM, and we know that omega is what? Under root of k by m. Do you remember that? Today only we have derived this equation. Omega is equals to under root of k by m, squaring both sides, so it is m omega square equals to k. So you can write down m omega square to be k. So this kinetic energy is what? Half k a square cos square omega t. This is the expression for kinetic energy, okay. This is the expression for kinetic energy. Similarly, we can also find out the potential energy of this particle. So potential energy is what? Half kx square. Potential energy of the particle is what? Half kx square. This is the change in potential energy from the mean position. So I have assumed the potential energy at the mean position to be 0. Assuming potential energy at mean position equals to 0, then the change in potential energy from mean position, when the particle is displaced by the displacement x, then the potential energy increases by an amount of half kx square. So this is the change in potential energy from mean position. So this is half k and x is what? A sine omega t, okay, and this is square. So this is half k a square sine square omega t. So this is the expression for the potential energy of the particle from the mean position, change in potential energy of the particle from the mean position, assuming potential energy at mean position to be 0. So this is expression for potential energy, and we have to write down the total mechanical energy. Total mechanical energy, then it should be what? Adding kinetic energy and potential energy. Kinetic energy plus potential energy. And it is what? Half Ka square, taking common. Half Ka square I am taking common. And this is sine square omega t plus cos square omega t. Okay. And you know that by the identity this becomes 1. So total energy of the particle performing SHM is what? Half K square. This is total mechanical energy. So total mechanical energy of the particle is what? Half K square. This expression for kinetic energy and this expression for the potential energy. I hope this is clear to everyone. So we have got expression for energy, displacement, velocity, acceleration, everything. So kinetic energy is what we have written. Now we will see few questions and then we will get the better idea. It's been written that the xt graph of the particle performing simple harmonic motion is shown in the figure, and we have to find out the acceleration of the particle at t equals to 2 seconds. Here at t equals to 2 seconds, at this point we have to find out the acceleration of the particle. So how to find out the acceleration of the particle? How to find out the acceleration of the particle? Any idea? We know that the acceleration of the particle performing SHM is the function of its position, and it is written as minus omega square x. Okay, it is minus omega square x, and we know that acceleration is what? Minus omega is what? 2 pi by t square multiplied by x. So acceleration is what? Minus 2 pi by t. And what is the time period of oscillation? You can see that it is completing one cycle in 8 seconds. So 2 pi by 8 square multiplied by x. What is the position of the particle? It is 2. So this is 4. So this is minus pi square by 16 into 2. This is minus pi square by 8 meter per second square. Minus pi square by 8 meter per second square. That is the correct answer for this numerical. Just a minute. Okay. The value of x is not 2. I am sorry, by mistake here. Calculation error is there. It is into x minus pi square by 16. The value of x is what? This is time, right? This is t equals to 2. So when the time is 2, the position of the particle is 1. So this is 1. Okay, the value of x is 1. So this is minus pi square by 16 meter per second square. So minus pi square by 16 meter per second square. First is the correct answer for this question. So I hope this is clear. So by just looking at the graph, we can figure it out that the particle is performing SHM, and it starts from t equals to 0, and at t equals to 0 the position of the particle was x equals to 0, and as the time increases the position of the particle changes to 1, then it again becomes 0, then it becomes minus 1, and again it becomes 0. The particle come back to its original mean position. Okay, coming to the next question. The displacement of the particle executing simple harmonic motion is given by this equation. Then the amplitude of its oscillation is given by. Here you are supposed to find out the amplitude of the oscillation. So I am just giving you fraction of few seconds. Just think of this problem and figure out how you are going to do this. Okay. So we need to solve this question. The displacement of the particle executing simple harmonic motion is given by this equation. Amplitude of oscillation is required. So basically you have these three equations: a naught plus a sin omega t plus b cos omega t. Okay. So you have to find out the net amplitude of the oscillation. So how to find out then? One function is, you can see, this is sine function, this is cos function. I already told you that try to make them functions to be similar functions. Okay. So I'll convert everything in terms of sine. So y equals to what? A naught plus this is a sin omega t plus b sin omega t plus pi by 2. So you can see that this function and this function is having a phase difference of pi by 2, and their amplitude are a and b. Okay. So if you will see that there, if I'll draw by phasor diagram, this is a, right? This is a, and then b is having a phase difference of 90 degree. Okay. This is b, and the angle between them is 90 degree. So the resultant will be what? The resultant will be this one, under root of a square plus b square. Okay, this will be under root of a square plus b square. Now this SHM will be what? It will be reduced to y minus a naught equals to what? Under root of a square plus b square. So it's something like that, that this is the situation, right? That if it is an SHM, so let's say this is some a naught line. Okay, from here like SHM will happen, and this is a square under root of a square plus b square above this line, and under root of a square plus b square below this line. So the amplitude of oscillation will be under root of a square plus b square. So this is how we can solve this question. Okay. Have you understood this? The displacement of the particle is varying from a naught. So a naught is your baseline. So this is like your mean position. So maximum displacement from the mean position is what? Under root of a square plus b square. So this is a naught plus under root of a square plus b square, and this is a naught minus under root of a square plus b square. So this is your amplitude of oscillation. Done? Moving to the next question. A particle executes linear simple harmonic motion. Linear simple harmonic motion means what? The particle is performing SHM along a straight line. It is not rotating, right? We also have angular SHM. So we are not having the case of angular SHM here. This is linear SHM. Linear SHM means particle is traveling along a straight line path. Particle is traveling along a straight line path with an amplitude of 3 centimeter. So amplitude is 3 centimeter. When the particle is at 2 centimeter from the mean position, means the displacement from the mean position is 2 centimeter. The magnitude of the velocity is equal to that of acceleration. Then its time period in seconds will be what? So magnitude of its velocity is equal to that of the acceleration. So at x equals to 2, magnitude of the velocity, okay, velocity magnitude will be equals to that of acceleration, mod of v equals to a, okay, mod of v equals to a. So from here you have to find out the time period of t is required. So you can try this question and then I'll solve it for you. Okay, I'll solve it for you. Just give it a try. Just give it a try. Do it fast. Okay. Now I'll write down the equation. Magnitude of velocity is omega under root of a square minus x square, and this is omega square x. Just I'm writing the magnitude, okay? So I'm not writing the negative sign. So velocity magnitude is omega under root of a square minus x square, and acceleration is what? Omega square x. So solving this equation, I'm getting this as a square minus x square equals to omega square x square, okay? So from here I'm getting a square equals to x square common, omega square plus 1. The value of a is given, okay, and x value is also given. So this is, a value is what? 3, and x value is what? 2. So 3 by 2 square equals to omega square plus 1. So this is 9 by 4. 9 by 4 minus 1 equals to omega square, and 9 minus 4 is 5 by 4 equals to omega square. Omega is what? 5 by root 5 by 2. And omega is what? 2 pi by t, okay? So we have 2 pi by capital T equals to root 5 by 2. So from here t is what? 4 pi by root 5. 4 pi by root 5. So B is the correct answer, okay? B is the correct answer for this question. So now you can see the type of questions being asked are very, very simple. You have to just use the basic things and just using these expressions that I have already taught you today in this session, how to find out the V, how to find out the A. So you don't have to just mug up these situations. You have to understand this, these formulas by using some logic, that you know the displacement equation. You can differentiate it, then you can find out velocity, you can find out acceleration. You can write down velocity in terms of time. You can write down velocity in terms of position. Same in case of acceleration. Acceleration can also be written in terms of time. It can also be written in terms of position. So just writing velocity, acceleration in terms of time and position. Then you can write down kinetic energy expression. You can write down potential energy expression. You can use total energy conservation. And using this simple logic, you can try solving these questions. And you can see that these questions are too simple to be answered, okay? So just basic things are required. Now you can also give a try to this question. The particle is executing SHM along a straight line. Its velocity, distance x1 and x2 from the mean position are v1 and v2. The time period is required. So one expression you can write down as v1 what? Omega under root of a square minus x1 square. So a particle is executing SHM, and I am assuming that the time amplitude of SHM to be a, okay? And the velocity at x1 distance and x2 distance are v1 and v2. So we are talking about the same SHM. So amplitude will be same in both the situations. So v1 is omega under root of a square minus x1 square. In second situation, the velocity at the position x2 is given, and that is omega under root of amplitude remains the same minus x2 square. So we have these two equations. Just solving these two equations, we can find out the time period in terms of v1, v2 and x1, x2. So I'll tell you the answer for this question. And you can solve it complete. You can complete the solution, okay? The answer to this problem is you will get the first option A. Okay, you will just solve these equations, you will get it, okay? You will square both the sides. You can square both the side and then you will get it, okay? Coming to the next question. The oscillation of a body on a smooth horizontal surface is represented by the equation x equals to a cos omega t. So you can understand this thing. The equation of SHM can be represented by a sine function, or it can also be represented by a cos function. So you not need to mug up that SHM equation is always represented by sine function, okay, or represented by cos function. it have to be represented by a sinusoidal function. So either it may be a sine function or it may be a cos function. So both are correct, okay? Both are correct. But if you are remembering it at all, so just remember that if you are writing in terms of sine, so always do by writing in terms of sine. Or if you are writing in terms of cos, you can always write in terms of cos. Or if you understand the logic, then it does not matter like whether it is written as sine function or cos function. It's same thing for us. Here the x is displacement, t is time, here omega is the frequency of oscillation, which when the following graph shows correctly the variation of a with t. So acceleration versus time. Acceleration versus time. So we know that acceleration is what? Minus omega square x, and x is what? X is a cos omega t. So this is your a versus t relation mathematically. So if you have to draw the graph for this one, you can easily write down, okay? It is going to be a cos function. A versus t is going to be a cos function. So which of the following option is correct? It have to be C for Chennai, right? If you know that how to draw a cos function, so cos function is like this, okay? But it is a negative sign here, so it will be an inverted cos function. So it have to be C option Chennai. Let me check the answer for this one. Let me check the answer for this one. Yeah, definitely C only. The C option Chennai is the correct answer. Inverted cos function, okay? So if I'll just invert it, it will start from here and it will go like this. So this C is the correct answer. So just you can see that how I have done this question. They were asking us to find out the graph between A and T. So I've written a mathematical function which connects A and T, and then I've drawn a graph for that. So this is how you can approach this kind of problems, okay? So I have covered most of the concepts of this chapter, oscillation, okay? And I have give you a brief idea from just solving 2-3 questions. So I have added few more questions for you people as an homework. So you can try doing these questions, okay, in homework. And if you find any question tough, then you can write down in the comment box, and definitely I'll be more than happy to answer those questions in your reply to in the comment box, okay? So that was all from my side in today's session, and wish you all the best in your preparation. Keep hustling and keep working hard for the coming NEET exam, and I'm very sure that if you'll keep up the good work going on, definitely you are going to crack your NEET exam with a very good rank, and definitely you are going to get a very good medical college. So thank you guys, thank you for watching me, and I'll be coming here with some more sessions on some different topics of physics. And till then, bye bye everyone.